All right, I think it's time to get started. Welcome back. This is my last class of the semester. I hope it's your last class too. Is it your last class ever, some of you? All right, congratulations. It's a shame you have to spend your final hour with me, isn't it? I don't. I hope it's worth it. Um, so our exam is a week from today, May 11th at 11:30 a.m. in this fine room. I will expect everybody to be there in person. Um, you could all get A's, yeah. We'll see, I guess. Yeah. You probably won't all get A's. Just statistically speaking, yeah. That's all right. Um, okay, so that's that. Yeah, we also have just yesterday I posted our final homework assignment, which is going to be due on this same day. Um, so check it out. No, on the day of the exam. Yeah. Sorry, this same day, not meaning today. Yeah, a week from today. So check that out. Um, I would like to, for the last day, talk about the post-correspondence problem. This is what we started talking about last time, and I want to explain why you should believe that the PCP is unsolvable by algorithms. And then this won't take the whole time. So then I figured we'd do some kind of review for the test. And just for fun, I brought my final exam that I gave in this class last year. So we could, I'll hand that out and we can do some of those problems if you want, or talk about whatever else you would like to talk about. Okay, so anyway, I want to refresh our memory about the PCP, what it is. It's sort of a simple sort of logical puzzle where I give you a set of tiles like this. Each one has a string on the top and also a string on the bottom. And the goal is to arrange them, possibly repeating some of the tiles, arrange them in some order so that the string read across the whole top is equal to the string that you read across the whole bottom. So, and you have to start with this one with the fancy border around it is called the starting tile. All right, and in this particular example, this is the same example that I said last time. We have to start with that one, and then remember the vague strategy, although no algorithm can solve this problem, there's still some vague strategies which will work in certain situations. And the strategy that I have is I will look at the bottom one here. It says 1, 0. Since the string across the bottom has to match the string across the top, the next thing that I put here, it needs to start with a 1 because this next character, it has to be 1 followed by 0 followed by 1 across the bottom because it has to match what I see on the top, right? And it turns out in this case, to make this work, I'm going to use the first tile next. So now across the top it says 101010, and across the bottom it says 10101. I want to see another O on the bottom, and it turns out this is the way to make it work this time. So now when I look across the top, it says 1010101, and on the bottom it says 1010101. They're the same, so that means we have truly solved the puzzle. All right. So a valid solution is either show me an ordering of the tiles where this happens, or somehow demonstrate or conclude that no possible solution exists in any given problem. All right. So this, my goal for today, and this will not take the whole time, is I want to explain how any hypothetical PCP solver, which cannot exist, could be converted into a Turing machine sort of halting solver. Actually, more specifically, I'm going to say any hypothetical PCP solver could be converted into a machine or an algorithm or whatever to decide, given a Turing machine and a string x, say whether or not x is accepted. And this is equivalent to the halting problem, and so this is not possible to do. All right? So any hypothetical PCP solver could be converted into this kind of Turing machine solver, and that's what I'm going to try to explain, how exactly you would do that. But this Turing machine problem, this is not possible to do. This is impossible to decide with an algorithm, which means the original PCP must also be impossible to decide with an algorithm. That's the way the argument works. All right. This is actually the typical thing. You know, there are many problems that now we know are unsolvable by algorithms. If you are in the business of trying to think up a new problem which has no algorithmic solution, the typical approach is to somehow show that your new problem is somehow equivalent to the halting problem or equivalent to deciding if a Turing machine accepts something. Typically, in the real world, we don't prove directly that certain things are not solvable by Turing machines. We prove that they're the same as the halting problem, and that's how we do it. Anyway, let's do it. So I'm going to try and describe to you, given a Turing machine and a string, x, say, we can convert it, the whole situation, into a PCP problem, a PCP puzzle. So I'm just going to do one example. I'm not really going to, I don't think we need to talk in general about how you could do this for any example, because when we do one example, you'll see how it works. I'm going to go past the bar here. I'm going to write a Turing machine, and I'm going to give numbers. So there's just going to be 3 states, 1, 2, 3. And the alphabet, as usual, I'm going to use A and B. So here is my machine. State 1 has a loop that says BBR. Then it goes 1 to 2 with a AAR. It can go 2 back to 1 with a AAR. On 2, I have another BBR loop. 2 to 3 is blank, blank L. And then 3 is the accepting state. But I'm going to put this here. Ordinarily, we don't put any arrows on the accepting state, but I will say in a moment why. Anyway, this is my Turing machine. And this Turing machine, the language that's used for this is a Turing machine which clears the tape when it accepts. That's what those 2 looped arrows on the state 3 do. They go back through the whole tape and blank everything out. All right. So technically, in order to convert it into a PCP in the way that we're discussing, the machine has to blank the tape out at the end. If you ever had a Turing machine that did not blank the tape out when it accepts, it's always easy to convert it into one which does blank the whole tape out when it accepts. All right. So if you want to do this, you have to do it with a Turing machine that clears the tape. This is a technicality. It's not a big deal. All right? Let's ask ourselves, this question, is AB accepted? Now, in this particular example, it's easy enough to say whether or not AB is accepted, but this is the question actually in general. It is not possible to answer this question with an algorithm. If I just gave you any old Turing machine, imagine a very complicated one and a very complicated string, it's generally not possible to decide. The reason it's not, you can just try to do it and see if it's accepted or not, but you will have a hard time recognizing if there's going to be an infinite loop or not. That's the issue, really. Anyway, is it accepted? Well, on this Turing machine, maybe this is a cute little review. We can write a derivation. Derivation. I would write it like this. Remember this? We haven't done this in a little while, but the Turing machine begins in state 1. And the head, this says the head is just to the left of the A at the beginning of the string. All right? And you want to say what is the thing going to say next? You have to look on the diagram, decide what state it goes to, which direction the head moves in. What do you think? A to B, I think, is right. From 1A, B, that means you're sitting here and you see an A. You do this edge, AAR, so that A at the beginning stays as an A. The head moves to the right and goes into state 2. So now it is A to B. All right, from state 2, I do this BBR. I stay in state 2, but the head moves to the right again. So this now becomes AB2, right? Still in state 2, but it moved to the right. Now I'm looking at a blank, right? The 2 is pointed at a blank, so now it will move to state 3, and the head will move back to the left. So this looks like A3B, right? Leftward moves are always a little confusing to me on these when I'm writing it this way, but the 2 is pointed at the blank. It moves to the left and changes to a 3. All right, and now in state 3, I see this B. I blank it out and move to the left, so the next state will be 3A. And then I see an A in state 3. I blank it out, move to the left again. I see just 3. And then I'll just say this accepts, right? Something like, usually we don't write this part at the end, but I'm just trying to somehow write out the entire thing, including the blanking of the tape. All right? This is the derivation on the Turing machine. So the question in general about does the machine accept this or that? It's all about, is it possible to write a derivation like this, right? And I just did it, so in this particular case, it is possible. It does accept. All right? I want to translate this whole scenario into a PCP problem. So here's how you do it. I'm going to make the PCP tiles that represent pieces of this derivation. So like the strings that you're going to see on the tiles, they have A's and B's and 1, 2, 3s, and they also have that arrow. Like this big derivation that I made yellow there, little chunks of it are going to appear on the tiles. Okay, so I'm going to make PCB tiles that represents pieces of the derivation, and then your job solving the PCP is all about lining them up in the right way. All right, pieces of the derivation. There's going to be a lot of tiles. In this particular example, even though this is kind of a simple example, there's like 15 tiles maybe. But anyway, they come in simple categories here. So first of all, there are tiles representing the letters, and they're very simple. They're just like this, A. There's the A tile, the B tile, and then the arrow tile. They just look like that, all right? So this is one simple kind. We also have tiles which involve moves to the right. So you look back at the Turing machine, and every arrow which moves to the right gets a tile, and they look like this. So I'll write the first one and then say, 1A on the top and A2 on the bottom. So this represents the looped edge from state 1 to itself. This does not represent what I just said. It's the edge from 1 to 2. And the way when you look at this, the way you interpret this is, if I have the head pointed at A in state 1, after the next step, I will have moved the head to the right and it became a state 2, and the A still remains, but it's on the left. So this is kind of like a before and after snapshot of what happens right there near the A. When the 1 is to the left of the A, after you do that arrow, the scenario right in that area looks like A followed by 2. All right? And the other one. So there was also the looped edge. So 1B here. What happens after that if you're in state 1 and pointed at a B? After you do that looped edge, you should still be in state 1, but you're now to the right of the B. So now it's like that. All right? So each of these is just a little sort of before and after snapshot. So this was the looped edge on state 2. And then finally we had the edge from 2 back to 1, right, with an A. So this will say 2A, and then A1. I'm just now noticing I wrote this. It's wrong on my paper. 2A and A1. All right? These are all the moves to the right. Okay, what you see above is sort of the before, and below is kind of the after. All right? We also have a bunch of, and I didn't put the blanks. You actually don't need to put the blanks. What about moves to the left? These, unfortunately, you have to get a little fancier with moves to the left. It's because, so I want to look at something like this. Actually, this one is simple. If I have an A with a 2 on the right, I'm going to put a 2 and an A like this. And then let me write the first two, and then I'll explain where they came from. B2, 3B. So the first one, A2, 2A, it means if I'm in state 2, actually these have to do with the blanks. If I'm in state 2, so you should look at like this arrow here. Sorry, something's not right about this. A2. What are the leftward moves here? This is on my paper, but I think that shouldn't be there. Sorry, I'm going to get rid of that one. I'm not sure. Yeah, I don't know what I was thinking. Sorry about that. These are supposed to represent the leftward moves, which go blank, blank. I'm bombing on the last day. Sorry, give me a moment here. Yeah, I don't know what I was thinking with that one. I don't know. Both of these are bogus. B2, 3B. No, this one I actually needed. Okay, that one is legit. Sorry, I think just that first one was bogus. What this means, you have to imagine. Now I'm not going to write the blanks. Maybe I'll write the blank in blue, even though the blank doesn't actually appear on the tile. In red, I mean. B2. So the idea is, if you are in state 2 and you're looking at a blank, there's an arrow that says, from state 2, if you're looking at a blank, you should move to the left. It should stay a blank. You should move to the left and move yourself into state 3. And if there was a B to the left, this B to the left is kind of incidental, but it says if there happened to be a B on the left and you're in state 2 looking at a blank, you should move back. And now you should be in state 3, but looking at the B. And there's similarly with an A there. So this blank is not part of the tile. Similarly like this. The leftward move, you have to account for all the different possible things that could have been on the left side when you move to the left. So we have sort of two separate versions of the same idea here. I think this is what I meant on my paper. It should have said A2, 3A, not A2, 2A, which is what I had originally written. All right, sorry about that. Okay, another possible thing that could have been to the left of the 2 is you could have had 2 blanks on either side, and then it just looks like this. So this one represents the fact that if you're in state 2 somehow with blanks on both sides, then you should just change to state 3 and still be blanks on both sides. All right? Yeah. A2, 3A. Yeah. This means if you're in state 2 looking at a blank and you had an A to the left, it should change to state 3 and move to the left. All right? Okay, we need, unfortunately, a few more tiles. How about this? A3A. This means if you're in state 3 and you're looking at an A, but you also have an A to the left of you, it should blank the A on the right and move to the left and stay in state 3. So it looks like that. A3A, 3A. A similar one like this, B3A, 3B. This means if you're in state 3, pointed at an A, but there was a B to your left, you blank that A, move to the left, and now you're going to point at the B. All right? And then we need some which have B's rightmost. So we also have A3B, 3A, and A3A. I already did that one, sorry. B3A is what I mean. And 3B. All right? These are the leftward moves from state 3, which are blanking the tape. There's the two looped edges from state 3. B3B is what I meant. Yeah, sorry about that. B3B. All right, and finally, I think there are two more from this in this category. There's 3A, 3, and 3B, 3. This is blanking the last letter. All right, these are all the tiles for the leftward moves. It's kind of the leftward moves are a little more confusing, as you can tell, because I got confused. And then we have two more tiles. One represents the fact that we have the accepting state, and this is a weird one, but it looks like this: 3 arrow epsilon, where epsilon is, of course, the empty string. And then we have the special one for the starting state. You know, state 1 is the starting state, and this generates a special tile that looks like this. So for the starting state, you put epsilon at the top, and on the bottom, you put whatever the starting state actually is, which in this machine is 1, state 1, followed by the string that we are trying to make a derivation of. All right? The string here is AB. And that's why AB appears right here, because that is the particular string which we are trying to make a derivation of using the tiles. All right? And I want to show you how any derivation of this string corresponds uniquely to a solution in the tiles. I don't know about uniquely, but any derivation of the string will correspond to a derivation on the tiles. So our string derivation, unfortunately, I'm going to have to scroll past the tiles. Our string derivation can be done on the tiles. Check it out. So this was the starting tile, right? I should make it look fancy like that. So we must begin with that. Epsilon 1AB arrow, right? This is going to be my first one. I'm just going to, so that we still have it here, I'm going to write this derivation again. It was 1AB goes to A2B, right? And then AB2, and then A3B, and then 3A. I think I got this right. And then 3, right? That was the whole derivation, okay? Can we make that with the tiles, all right? What do we got to do? On the bottom, what we see here is you want to think of the tops and the bottoms as representing snapshots of this big string. And in fact, when you read the whole string across the top and across the bottom, it will add up to this whole thing, right? That's what the whole string is going to look like. You should think of the string as describing this derivation, but the bottom part is like one step ahead of the top part. When we begin, there's nothing on the top. And the bottom has already described the setup for the tape. Now, what I need to see first is the bottom begins with 1A. So when I choose my first tile to use, it needs to start with 1A on the top. And in fact, there's only one way you can do that in this example. You can see it's highlighted right there. I have to begin with the 1A, A2 tile. All right? And you can see, actually, if you read across the bottom, what I'm beginning to spell out is actually the same as the derivation that you see above, right? It begins with A2. What do I need to see next? Across the top, it needs to say 1AB, right? But across the bottom, just because I know where we're going, the next thing to see on the bottom, it says 1AB and then the arrow and then A2. The next thing I want to see is a B on both. So I'm going to use the letter B here. You use those single letter tiles to represent a part of the tape which is just staying the same in that step, right? What changed was this first part that tile represents, but then the rest of it changed. The rest of it stayed the same. And then I put the arrow, because the arrow goes in both fronts. And now I'm going to indicate the tile for the next step. The next step was when this 2B here, this 2B turned into a B2. And there is a tile for that, right? Isn't there? It's this one, 2B and B2. So that's the next tile that I use here. It's easy enough for me to do this because I already know what the derivation is supposed to be. But what is sort of unsolvable about this problem is if you don't already know what the derivation is supposed to be, then finding the derivation is really equivalent to finding the PCP tiles. That's the whole point of this. Anyway, 2B, B2 is next. Yes, thank you. I'm going to put the A tile because in this step, the A at the beginning is not modified. Yeah, thank you for that. I'm glad they're paying attention more than I am. Okay, and then do what I said before, 2B, B2, right? Then I want the arrow, because that was, again, sort of one step, all right? Next, what I'm coming up to next is this step here. I did the arrow. So across the bottom, I want it to say A3B, while the top is still one step behind. It's going to say AB2. So that means I have to put the A first. And then on the bottom, I want 3B, and on the top, I want B2. But that is a tile, isn't it? B2 and 3B. It is. It's the first leftward move that I wrote there. So I'm feeling pretty good about this. Then I put the arrow, because that was another one chunk there. All right. Next thing I want to see on the bottom, which is one step ahead, should be 3A. And on the top should be the previous thing, which is A3B. Is there a tile like that? I think there is. That was one of the leftward moves, right? A3B and 3A. Feel like I'm getting lucky every time that there was such a tile. It's because I know what the derivation is supposed to be. The fact is, finding the derivation in the first place is equivalent to finding the tiles in the first place. So if I already know the derivation, you can convert it into the tiles. That's the whole point of this exercise. All right, next comes the arrow again. So I have to go down here. And now, actually, the end here, on the bottom, it should just be a 3. And on the top, I want to see 3A. And that was, again, one of the leftward move tiles, I think. And then, almost done here, I put the arrow. Now, at the very end, I want to see nothing at all in the bottom, but I have to somehow end up with just 3 on the top. And that is the accepting state tile. So I put my final tile here is this. And that's it. Now, if you this is a solution to the PCP. If you read the string across the top, it's the same as the string across the bottom. All right? So, in conclusion, the moral of the story here is being able to figure out the tiles is actually equivalent to being able to know what this derivation is. And therefore, the two problems are the same as each other. So, no algorithm can solve the PCP. PCC. All right, that's it. The end. Any thoughts about that? Any questions? I think it's interesting. Thank you for your, I will say, just like Biden at the end of his big speech to Congress. Did anyone hear his thrilling conclusion? He said, "Thank you for your patience." Those are the last things he said. I like that. Usually they go out on, God bless America or something. He said that. He said, God bless America. And then he said, and thank you for your patience, which I appreciated. All right, so we got 20 minutes on the clock. I think we can talk a little bit about the final exam. I think I said before, but the final exam covers everything. I'm going to say at least 1/3 of it will focus on the new stuff, which is the Turing machines. And then the rest of it will be anything goes. And you have 3 hours to do it, as always. I'm going to make it maybe a bit longer than our other in-class tests, but I'm not going to try to make you fill the whole 3 hours. So you should expect it to be maybe 1.5 times what we had for our in-class tests. You can take the whole 3 hours, but I'm not going to try to blow you away by asking way too many questions. So I'm not sure what would be most helpful for our remaining 19 minutes together. Like I said, I have this test that I gave last year. Not all the possible topics will appear on this test. So, I hope you can do all these problems, but don't be fooled into thinking these are the only things that might be on the test. Anything that we've done the whole semester could possibly appear on the test. I thought maybe we could just, I could hand these out and you guys could kind of work on them and I could just sort of walk around and see how you're doing. Although before, and I'm happy to do that, before we do that, does anybody have any particular questions or maybe something that you really did want me to do an example of or something? It's still a week before the test, so I don't have a schedule for when I will be available for questions, but I would be happy to talk to anybody over the next week. If it turns out you do have questions come up, just let me know and we can set something up and I'll reach out to you. I'm going to email these out to everybody later so you'll have it that way also. I also don't have answers written up for these questions, but I would be happy to look at your answers and tell you how you did. For the folks in the Zoom, I'm gonna chat this thing. Is there anybody there? Yeah. Sorry, I won't be able to talk to you guys individually. I will put this test in the chat. I'm working on it. All right, I just chatted it. I hope you got it. Later on, I'm going to send it by email in case it didn't work. You guys in the Zoom have any specific questions you wanted me to talk about? Nope. All right. All right, great. Thanks for the chat. There's one on the